10th Standard Geometry, Chapter 3, Circles, Module 5. In this module, we'll study about inscribed angles, the inscribed angle theorem, and its corollaries. Let us recall. We know that an angle whose vertex is the center of a circle is called as the central angle. Then we study the definition of measure of an arc. We know that the measure of a minor arc is equal to the measure of its corresponding central angle. So, whatever the measure of the central angle is, corresponding to that central angle will be the minor arc, and both of them will have the same measure. Then, measure of a major arc. We use the formula 360 degree minus measure of its corresponding minor arc. So if you know the measure of the minor arc, by this formula we can find out the measure of the major arc. Measure of a semicircle is 180 degree. Third, when two arcs are of the same radius and same measure, they are congruent. Fourth, when only one point C is common to arc ABC and arc CDE of the same circle, then we can say measure arc ABC plus measure arc CDE is equal to measure arc ACE. This was the property sum measures of arc. Fifth is a theorem. Chords of the same or congruent circles are equal if the related arcs are congruent. Sixth is a converse of the theorem that says arc of the same or congruent circle are equal if the related chords are congruent. Inscribed angle. Let us understand the definition of inscribed angle with the following figure. In the figure, we can see that angle DCB is inscribed in the arc DCB and it intercepts the arc DB. In the figure, the red portion is called as the intercepted arc, and we can say that angle DCB intercepts the arc DB. Therefore, we can say angle DCB is called as an inscribed angle, and it is inscribed inside the arc DCB. Arc DB, the red portion, is called as the intercepted arc. Inscribed angle theorem. Let us understand the statement of the theorem. The theorem states the measure of an inscribed angle is half of the measure of the arc intercepted by it. Let us understand the statement of the theorem with the following diagram. It is given that in a circle with center O, angle BAC is inscribed in arc BAC and arc BDC is intercepted by the angle. So it is said that BAC is an inscribed angle and it is intercepted by the arc BDC. We have to prove angle BAC is half of the measure arc BDC. So the inscribed angle theorem states that the inscribed angle is half of the measure of its intercepted arc. In this case, angle BAC will be half of the arc BDC. So we have to prove this in the theorem. Let us start with the proof. In triangle AOC, side OA is congruent to side OC, the reason being they are the radius of the same circle. Therefore, angle OAC is equal to angle OCA, as it is by theorem of isosceles triangle, or we can also say that angles opposite to equal sides will be equal. Let us consider angle OAC and angle OCA to be x. We'll number it equation 1. Now, angle EOC will be equal to angle OAC plus angle OCA. This we can say by exterior angle theorem of a triangle. That is, angle EOC will be equal to the sum of the two exterior angles. That is, angle OAC plus angle OCA. Therefore, OAC and OCA, both we have considered it to be x, so we can just substitute it, x plus x, which will be 2x degrees. Therefore, I can say that angle EOC is 2x degree. But angle EOC is a central angle, and the measure of angle EOC is 2x degree. Now, we know the property that the measure of the central angle and the measure of its corresponding arc will be the same. Hence, the measure arc EC will be 2x degree. Therefore, from 1 and 2, we can say that angle OAC will be equal to angle EAC. Hence, it is half of measure arc EC. We'll name this as equation 3. Similarly, drawing segment OB, we can prove that angle EAB will be half of measure arc BE. We'll name this equation as 4. Therefore, from 3 and 4, we can say that by adding the right hand side and the left hand side, we get angle EAC plus angle EAB is equal to half of measure arc EC plus half of measure arc BE. If you look in the diagram, angle EAC plus angle EAB together, it forms the angle BAC, and arc BE plus arc EC together forms arc BC. Now, by taking half common and by adding arc EC and arc BE, we get arc BEC. Note one thing, arc BEC is same as arc BDC. Therefore, we replace it with BDC. Therefore, angle EAC is equal to half of measure arc BDC. We name this as equation 5. Note that we have to consider 3 cases regarding the position of the center of the circle and the inscribed angle. The following are the 3 cases. The center of the circle lies first on one of the arms of the angle, second in the interior of the angle, and third in the exterior of the angle. Out of these, first 2 are proved in the previous part, that is 3 and 5. Now, we will prove the third one, that is, if the center of the circle lies in the exterior of the angle. In the figure, angle BAC will be equal to angle BAE minus CAE. So if you notice in the figure properly, BAC will be equal to BAE minus CAE. Now from 3, we know that BAE will be half of measure arc BCE and CAE will be half of measure arc CE from 3. Therefore, from here in this step, we can take the half common outside. what we'll be remaining with is measure arc BCE minus measure arc CE. Now, if you notice in the diagram, measure arc BCE minus arc CE will be arc BC. So, we replace this with arc BC. Therefore, measure angle BAC will be equal to half of measure arc BC. This will number it as equation 6. If you notice, in each of the three cases, we have proved that the central angle is half of its corresponding intercepted arc. The above theorem can also be stated as follows. The measure of an angle subtended by an arc at a point on the circle is half of the measure of the angle subtended by the arc at the center. Corollaries of inscribed angle theorem. The first corollary is angles inscribed in the same arc are congruent. Let us understand the statement with the following diagram. Here in the diagram, a circle with center C have two angles inscribed in the same arc, angle DCB and angle DEB. Now, since both of the angles are inscribed in the same arc, these two angles will be equal. Therefore, angle DCB will be equal to angle DEB. Hence, angles which are inscribed in the same arc will be congruent. The second corollary is angles inscribed in a semicircle is a right angle. Here, the circle with center A, we can see CB will be the diameter and CDB is a semicircle. So the diameter divides the circle into two halves, and the upper half and the lower half are called as a semicircle. Now the above arc, that is arc CDB, is a semicircle. Angle that will be inscribed inside the semicircle will be the right angle, will be a 90-degree angle. Therefore, angle CDB is a right angle. Hence, we can say that angles inscribed in a semicircle is a right angle. Cyclic quadrilateral. Let us understand the definition of cyclic quadrilateral. If all vertices of a quadrilateral lies on the same circle, then it is called a cyclic quadrilateral. In the figure, at the circle with center A, we have the quadrilateral DEBC. You note that each of the vertex of the quadrilateral lies on the circle. Hence, DEBC is called as a cyclic quadrilateral. Next is the theorem of cyclic quadrilateral. The statement of the theorem is opposite angles of a cyclic quadrilateral are supplementary. Given a circle ADCB is a quadrilateral and all of the vertex of the quadrilateral lies on the circle. Hence, it is called as a cyclic quadrilateral. We have to prove that the opposite angles of the cyclic quadrilateral are supplementary. That means the sum of the opposite angles is 180 degree. So we have to prove that angle A plus angle C is equal to 180 degree and angle B plus angle D is equal to 180 degree. Proof: arc ABC is intercepted by the inscribed angle ADC. Therefore, by inscribed angle theorem, angle ADC will be half of the measure arc ABC. We number this as equation 1. Similarly, angle ABC is an inscribed angle. It intercepts arc ADC. Therefore, by inscribed angle theorem, we can say that angle ABC will be half of the measure arc ADC. We'll number this as equation 2. By adding 1 and 2, we get angle ADC plus angle ABC is equal to half of measure arc ABC plus half of measure arc ADC. By taking the half common, we get measure arc ABC plus measure arc ADC. If you notice in the circle, arc ABC plus arc ADC forms the entire circle, and we know that measure of a complete circle is 360 degree. Therefore, we replace this by 360 degree. So we get half into 360, which is 180 degree. Therefore, we can say that angle D plus angle B is 180 degree. Similarly, we can prove that angle A plus angle C is equal to 180 degree. Hence, the opposite angles of a cyclic quadrilateral is supplementary. Next is a corollary of a cyclic quadrilateral theorem. The corollary states that an exterior angle of a cyclic quadrilateral is congruent to the angle opposite to its adjacent interior angle. So, in this case, in the figure, the exterior angle is CBF, and that is congruent to its opposite adjacent interior angle, which is angle EDC. So, these two angles marked in green will be congruent to each other. Hence, an exterior angle of a cyclic quadrilateral is congruent to the angle opposite to its adjacent interior angle. In this case, it is angle CBF congruent to angle EDF. Next is a converse of cyclic quadrilateral theorem. The converse states that if a pair of opposite angles of a quadrilateral is supplementary, then the quadrilateral is cyclic. So the cyclic quadrilateral theorem says that the opposite angles are supplementary, and the converse says that if the pair of opposite angles of a quadrilateral is supplementary, then that quadrilateral is cyclic. So in this case, you can see the quadrilateral A, B, C, D, and the angles are given. If you notice, the sum of the opposite angles, in this case angle A plus angle C, is 100, and this is 80. You add it, you get 180 degree. Similarly, if you add angle B and angle D, that is 75 and 105, you get 180 degree. So in this case, the opposite angles are supplementary. So by the converse of cyclic quadrilateral theorem, we can say that this quadrilateral A, B, C, D will be cyclic. That means the vertex of the quadrilateral will lie on the circle. Let us recall. First, the measure of an inscribed angle is half of the measure of the arc intercepted by it. This is the inscribed angle theorem. Second, angles inscribed in the same arc are congruent. Third, angles inscribed in a semicircle is a right angle. Fourth, if all vertices of a quadrilateral lie on the same circle, then it is called a cyclic quadrilateral. Fifth, opposite angles of a cyclic quadrilateral are supplementary. This is the cyclic quadrilateral theorem. Next, if a pair of opposite angles of a quadrilateral is supplementary, then the quadrilateral is called cyclic. This is a converse of cyclic quadrilateral theorem. Seventh, an exterior angle of a cyclic quadrilateral is congruent to the angle opposite to its adjacent interior angle. This is the corollary of the cyclic quadrilateral theorem.